Hi, welcome to Fun at Pi videos. This is DC here. In this video, I'm going to show you how to use the Transceive command using OMNIKEY 5022 reader writer. If you have not seen my last video, I would advise you to see my previous video, and this video is the continuation of the previous video. If you look at the documentation of OMNIKEY 5022, there is a section about the transparent session commands. If you read the documentation, you will see these are the various commands available for us, for the developers. The enter transparent session, this is the first thing we call before we run any other command. The exit transparent session, this is the command you execute before you come out of the transparent session. There is a command to set the protocol. If you are working with different protocols like ISO type A, type B, or ISO 15693, you'll end up using this set protocol command. So I'll be using this command when I make videos on ISO 15693. This command you can use to set the transmission and the receiving speed, and there is a command to turn off the RF field on and off. And this is the command that the Transceive command is what I'll be explaining, probably speaking about this command in more detail in this video. So using the Transceive command, you can send any card specific command and return and get the response from the card. I did show you how to use these commands in my last video, so please take a look at my last video. So this is for the developers and for the students. So you have to understand the command structure. You have to read the documentation of 5022 if not once, a couple of times. So you have to understand. So this is I just want to show you the documentation. So this is the documentation you can download from the manufacturer site, and there is a section on Transceive. Now this command is pretty straightforward, but there are few things which you have to understand in detail. In fact, we never understood some of these bits when I did the last video, so we are better off in this video. So here, if you look at this command structure, you can't do anything with the first few bytes. They're all fixed numbers, and also this part of the command is again specific to the card you're using. If you're using a MeFair EV1, you'll end up using that. If you're using a DeskFire, you'll end up using the DeskFire commands. Now I'll be showing more about these two bytes, the TX, RX, and the valid bits. There's one more section called the timeout. I just can't figure out how to decide what should be the timeout. So you can leave it to 000, or you can give any higher number. But only thing you have to keep in mind when you use this timeout is the MSP of the value is sent first. That's what the documentation says. So there are 5 bits in the RX TX flags. If you have done any low level programming like sending the REQA or REQB or anti-collision commands, you'll understand. And also if you read any documentation on ISO 1443A, you understand about the CRCs. Now there are 5 bits of important here. It is the bit for the CRC. The TX is the transmission side CRC. So it means if you think is this a reader, this is the OMNIKEY 50 reader. So do you want the reader to compute? And so this is your card, the RFID card. Do you want the reader to compute CRC along with the data? That's what it means. And the parity bit also means, do you want the reader to compute the parity bit along with the command or the data? And the last two bits, the RX CRC and RX parity, do you want the reader to check if there is any RSC sent and whether RSC is valid or not? And also, do you want the reader to check the parity sent by the card? And you have to go in depth about these two concepts, because sometimes you want the reader to compute the CRC. There are some commands where you don't have to send the CRC. And also, sometimes you get a response from the card without the CRC, or you get the response from the card without the parity. So take for example, the card does not send CRC at all, then you have to set this as a 0, because the response doesn't have the CRC, and you do not want the reader writer to check for CRC. So you just have to get used to these concepts in order to do a good programming. The next thing is about the validity, the valid bits. There are not many options here. Either you set it all zeros, it means the last byte of the transmitted data has got complete 8 bits, or you can set it to any number with the 3 binary digits here, 0 0 0 2 1 1 1. We can go up to 0 0 to 7. So telling the reader to send just a few bits as a last byte. And other thing which is more important here is the response you get for the transceive. So all responses starts with the STS and RXP, and also the actual response, and followed by 9000 or any error. And until we did the last video, we never sure about how these bits are used. So I'm going to show you a couple of examples and make you understand the STS and RXP. Again, in a documentation is already mentioned here. STC 00000 is what we expect because a success, 01 is a failure, or 03 is a buffer full, and so on. And here 07 is a HID parity error. So if you refer back to the what I just mentioned, if you set this parity bit 1, and if the response doesn't have the parity, you will end up having this bit. And this RXB, this tells you the number of bits in the last byte. This is very interesting, and I'm going to explain you soon. Okay, so with this background, let's say what I've got next. I also have a software developer's guide on OMNIKEY 5023. If you look at this documentation, you don't see any section on the transparent mode. So because I don't have this reader writer, I'm not sure whether the transparent mode is supported by 5023. So if you're in a doubt, I would advise you to contact OMNIKEY support guys. So one thing I would appreciate is the support, the technical support of OMNIKEY is fantastic. So you will get lots of emails from them, with lots of answers as well. So please check with them before you buy 5023. So you already know now what is TXRX flags. You know what's the CRC thing. Now you know about this RxCRC and TXCRC and parity, RxCRC and parity. Also mentioned about the valid bits. So this basically telling the reader that to transmit less than a byte size. So for example, if you look at the documentation of REQA, it says the command REQA needs sending using only 7 bits, not 8 bits. And also some of the responses from, say, the MeFair attacks, sends you a response which has got just 4 bits. It's 0A. It just sends you 1010. So you are getting 4 bits of responses. So again, there's no parity here, there's no CRC here. Okay, so I'll be using a UID changeable tag in this video, and this video is not about showing how to use UDID changeable tag. It's just because I found it, this tag you can send some low level commands. And if you want to know more about UDID changeable tag, you can see my other videos in my channel. So this is a documentation from MIFARE classic tag, and I would like to show you this 7 bits command size. If you see this REQA and WUPA commands, the command is 26 and 52. It says these commands need sending using only 7-bit. Now in fact the 5022 documentation itself, they do have an example. If you just scroll down here, further down, now there's an example on how to use this direct commands. Okay, look at that. So if you go scroll down my page 75, there is an example on how to send how to use this transparent communication. And also look at this REQA example where you can see the bit here 07 means send 07 bits, and also the 0A means just look for only the CRC or something like that. So this is the software we have been using in all my videos. I'm just going to show you something which I used in my previous video. Now I've got a MIFARE UltraWide EV1 tag here, and I'm going to go to that screen. I'm going to activate. I'm going to read and try to change the value of a pack value. It doesn't matter. You just have to make sure I'm trying to use the transparent command. So this is exactly what I showed in the previous videos. And in fact, in my previous video, I also said that to ignore these responses, because if you look at this, the value of the RX, TX, and the next number, I'm not sure how my developers got these numbers, but somewhere they must have got as an example from the documentation. Now by passing 1F and 08, you get this as a response. And I still remember I mentioned to ignore this, because I know the write is done already. The write is successful. If you try to say read the value of the pack, or pack value cannot be read, just try to authenticate. So authenticate, you can see the pack value here. The pack value is the hexadecimal number, so the pack value is right here. So you can see here the pack value matches whatever written. Okay, so we got the 06 and 08. If you look at this documentation from 5022, go to page number 70. So the first 2 bytes corresponds to STS and RXP. So 06 was a timeout, and 08 was the number of valid bits in last byte. So it says it has received 8 bytes. So then after so just recently we came to know that we are wrong. Okay, so because the write command of MIFARE UltraWide EV1, so I'm going to show you the documentation of this is the write command of UltraWide EV1. If you look at this, this is the command that is sent to the card. So the command has got the CRC as well. So we must have the CRC bit on the RX side set to 1, and because this is a type A, the parity is also required. It's also set to 1. And the response is either ACK or NAK. Now ACK NAK is a 4-bit value. If you look at this table here, it is a 4-bit value. ACK is a 10 or 1010. So what we need is, we need the CRC to be enabled, parity enabled from the TX side, not the receive side, from the transmission side, and we do not want the CRC or the parity on the receive side. So I've got a different version of the same software which I'm going to show you now. So I'm going to do exactly the same operation, but this time with a different version of the software. So I'm going to write the pack value. Pack cannot be more than 30,000. Oops. Yeah, sorry, it's a 16-bit unsigned number. I'm wrong here as well. So okay, so here if you look at this, here I'm passing 03 as the TX RX flag. So 03 means to have only the last 2 bits, which corresponds to, if you go back to the documentation again, so I'm setting only this and this bit, which is to compute the CRC and also to send the parity, but none of these fields are set. So there's one more thing called EMD suppression enabled, which I'm not very sure what exactly is this. Probably now we'll come to know about this gradually. Now you just have to set the RX CRC, sorry, TX CRC and TX parity, only these two. So if you convert this to the binary, it will be now 00011 or 03 in hex. So when you send this, and this, I'm still sending all the 8 bits in the command. So this set to 00. So look at the response. This is much cleaner now. So you got 00. So that's a very, very positive response. 00. It's a HID success. And the next value was 04. 04 means the number of valid bits in last byte, which is 4 bits. That's exactly what the documentation says. And this is followed by the actual response, that's the 4-bit value, and this is 9000. This is the success command of this APDU. Okay, so this is what you have to keep in mind when you start using the Transceive command. Now I'm going to show you next the UID changeable tag. If you choose UID changeable in the screen, activate. So in order to use this UID changeable tag, you have to send what are called as the backdoor commands. Now I'm going to hit this button. You can see here these 3 commands are related to this UID specific UID changeable card. The first thing we have done here is to first enter the transparent session. So this is the command used. Then send the halt command. So here again I've taken this as an from the example which is in the documentation. So you just have to understand the TX-RX bit here is set to 0B, which is 1011. So that's the CRC computed during the transmission, the parity of the TX, and there is no CRC on the reception, and there is a parity on the reception, followed by the 0A, sorry, here, followed by 00. This is all the 8 bits. If you look at this is the halt command. So the last byte of the command is sent with all the 8 bits. Now the response, again, you can ignore the responses. Now we just don't know why the response is 0600. It is possible because the card is driven to the halt state. Maybe you don't expect any response when the card is halted. The next two commands are pretty interesting. The first backdoor command is the 40, and this needs sending using the 7-bit size. You can see here the command to do that is 0A, which is 1010. So we have got no CRC, we have got a parity sticked while transmitting, no CRC checked from the response, but the parity is checked from the response. Followed by the 07 is we want the command 40 to go as a 7 bits, not the 8 bits. Now the response is pretty clean here. It is a 00, it's a success, followed by 04, which indicates it's a 4-bit response, which is the response is 0A, that's an acknowledgement. The command 43, this needs going as a 8-bit, so we have got exactly same as above, 0A, with the no CRC for transmission, no CRC for reception, but the valid bits is set to 00, which is this 43 is sent as an 8-bit. If you want to know exactly what this 7-bit and 8-bit thing is, say 43, the hex equivalent of that is 0013. This is the 8-bit hex equivalent. When we ask the system to send only 7 bits, it's only this part of the command is sent. The last 0 bit is ignored. Now even here also the response is very positive. We got 0004, 0A. Now I'm going to quickly show you the other commands that are used here. Read, because this is a UDID changeable tag, you don't need any authentication. So here in case of read as well, you just have to check this one, 0F. Here the CRC parity for both reception and transmission are set to 11. I have not used the EMD bit here. So the response is pretty again very successful. 000 is a positive response. Now I'm going to change the UID here, change this to 25 and write. You got a message saying UID change is successful, but activate the tag again. Now if you look at this command structure, now these are the card specific command. If you look at any documentation on MIFI cards, so I'm going to show you the one. It's a write command you have to check. So I'm using this MIFI write command. Write is done in 2 steps. In the first step, you send the address, command address and the CRC, and what you get is just an acknowledgement. Again, keep in mind you're getting a 4-bit as a response, followed by the 16 bytes of data and the CRC. And I think all these MIFI cards, the parity is always sent, so you have to make sure the parity bit is always 1. And on the response, you get only either a 4-bit ACK or NACK. Again, you have to, there's no CRC in the response, but however, the parity bit, I think it's always set in case of a MIFI. Now, if you look at this command structure here, so we're using 03. So where this says there is a, I'm not, in fact, the parity is not set for the response side. It just is 00. It's a 0011. This is the CRC and the parity for the transmit, whereas it's 00 for reception. In fact, with this pattern, it did work. Probably if you want to experiment more, try to set this as 1 and see if you can still get the same responses. So, but these are when you work at a bit and byte level, where probably you just have to stick with the whatever data works for you. Now the response is acknowledge, positive acknowledge, and the second is again I'm sending with the 0011, saying that the CRC and parity is used during the transmission, but I'm not bothered or not checked in the response, and the response is successful again. So the later part of video, and I'm just going to show you the using this UID card. So because we have changed the UID of this tag, if you reactivate, you get the modified UID. So I'm going to show you to read this entire tag. No, sorry. So whenever you hit the activate, you have to run this backdoor command. Now read the entire tag. Is everything successful? I'm going to transfer this entire this data to one more tag. This is again a UID changeable or rewritable tag. I'm going to activate that. If you look at backdoor active, if you look at the read, the tag is different, whereas I'm going to write this entire 64 blocks of data. If you hit write entire tag, now you'll see a series of write commands here. So every 16 byte requires part 1 where you tell the A0 and the block number and the 16 bytes to write. In all these cases, you should see a positive response like 0004 A0. If I activate, you can see that this is the UID of that. Okay, so I think that's all in this video. So this video mainly focused on the transceive command as well as the value of TX, RX and the validity bits as well. So thanks for watching.